Hello guys, welcome on Tesla Adventures. In this video we are going to discuss the concept illustration problem first, in which we'll be finding out the time period of a small SHM of this mass as well as this length y for which this mass remains in equilibrium. First of all, let me tell you the scenario. In this question you can see that there is a inverted V shaped wires, two wires, and there is a movable wire which is attached with these two wires, and this wire can move on these wires while being attached to them, and this triangle formed is being dipped into a soap solution liquid which creates a film which is of triangular shape, and the half apex angle of this triangle is alpha. This one is alpha. The value of surface tension is T, and there are two free surfaces. The first one is above this frame and the second one is below this frame. Now first of all we have to find out this value of y for which this mass will stay in equilibrium, as well as in second case we'll be displacing this mass by a small distance, and then we'll be finding out the time period of a small SHM of this mass. So let us start the first case. Let us see that obviously this length, if this length is x, and there would be a cohesive force acting on this wire applied by the liquid film in the upward direction, which is also called as surface tension force, and this force will be balancing out this mg. Okay, obviously. So let us see that in equilibrium of wire, this cohesive force will be balanced by mg, and the cohesive force will be 2t into the length is 2x, and that is equal to mg. So 4t into x. Now we can say that x upon y will be equal to tan alpha. So x will be equal to y tan alpha. So this x will be y tan alpha, and that is equal to mg. So the value of y in equilibrium from this equation, the y in equilibrium will be equal to mg upon 4t tan alpha. This is the value of y in equilibrium. Now in the second case, in which we have to find out the time period of SHM, let us draw the scenario first of all. So this is the wire frame, and this half angle is alpha. This half angle is alpha, and the movable wire is this one, and initially this wire was at height y, and now we have displaced this wire by a distance of dy in the downward direction. This is y. So due to this displacement, the length of this wire which is inside this triangle, which is experiencing the cohesive force, is increased because the area of the film has increased. So this increase in length is dx, and this is the mass m. So we can say that this angle is alpha. So tan alpha is equal to dx upon dy. So dx is equal to dy tan alpha. Okay, and we obviously know that initially obviously this length is still x and this is still x, and the cohesive force acting on this length is balancing out mg. But now there would be a greater amount of cohesive force acting on this length and this length, which would be responsible for SHM of this mass, and therefore the additional cohesive force developed will be the surface tension 2t into the additional length dx. In fact, the additional length will be 2 dx, because this is dx as well as this is dx. So this additional force is 4t dx, and this force will be balancing, this force will be responsible for SHM, and it would be equal to m omega square dy, where dy is the additional displacement which we have given to the wire. So df 4t into dx is dy tan alpha, and that is equal to m omega square dy. So cancelling this dy and dy, we can say that omega will be equal to under root of 4t tan alpha divided by m, and omega is 2 pi by t. So t will be equal to 2 pi under root of m by 4t tan alpha. This is the time period of SHM of this wire, and you can see that we have not assumed that dy is very small. Whatsoever be the value of dy, the force will be proportional to dy only, linear power of dy, which means that for any value of y or dy, this wire will perform a simple harmonic motion. So the time period will be this one in any case. Thank you. And in the next video, we'll be bringing some more interesting concepts and concept illustration problems of SHM. Thank you.